have exponential growth and exponential decay. The idea of today, we're going to have to write and evaluate expressions. We're going to graph one, too, just to show you what it looks like, to remind you. So if we have something like growth that doubles every year, can be modeled using a function with a variable as an exponent. So the idea is it's 2, you're doubling every year, where t is equal to the number of years, right? Oops, I'm not exactly in the frame, am I? Okay. And then this idea of having the variable as an exponent is the idea of an exponential function. Remember, 2 to the t power is different than t squared. If I had t squared, what type of function would that be? Anything with a squared is parabola, which is the U-shaped function is a quadratic function. Okay. Anyway, the parent exponential function is b to the x power, where the base is b. And that's usually a constant meaning just like a number. A constant just means a number. And the exponent x is the independent variable. So that should hopefully make sense. So once you have your function f of x equals b to the x power, then it says the graph of the parent function 2 to the x power is shown. Well, we don't have that yet, so I'm going to make a table real quick. Remember, when in doubt, if you don't know how a graph looks, you should just make a table. And then this is something that a lot of you probably don't remember. So if I have my base 2 to the negative second power, what do I need to do with negative exponents? Well, I flip the fraction, which makes the sign positive, right? So then I'd get 1/4. I think we were both saying the same thing here. So I would have negative 2 comma 1/4. I'm going to put that like really close to the x-axis. 2 to the negative first power should be 1 over 2 to the first power, which gives me 1/2. Anything to the 0th power is a 1. We just learned about that property in Algebra 1 today. So remember, anything to the 0th power is 1. 2 to the first power is 2. 2 squared is 3, or 2 squared is 3. Math is hard sometimes. So I have 1 comma 2, 2 comma 4. 2 to the third power gives me 8. So 3 comma 1, hang on. That was 5. Sorry, I counted wrong here. 1, 2, 3, 4, 5, 6, 7, 8. So you're going to see this shape appear. Right? Exponential functions either grow, so they get bigger, or they start big and then they decay, right? If you're looking at the domain, remember the domain is the x values. Do you see how there's arrows in both directions on the x-axis? I could have negative x values, I could have positive x values, right? That means my domain could go from negative infinity to infinity. So remember, this is interval notation. You could also say all real numbers. Remember, that's a fancy R with an extra line through it. Or you could say x is between infinity and negative infinity. So we have the 3 different notations I would be fine with you using. Could also do set builder, but I'm not expecting you to remember that one, right? This is an R, so it means all real numbers, but it has an extra line through it to indicate that it means all real numbers. Yep. But if we're talking about the range, in the y direction, It could go up and up and up forever, right? But looking at the bottom number, so if we go up and up and up forever, that means my upper boundary is infinity. What's my lower boundary? What's the lowest it could go on the y-axis? You see that? On the y-axis, it kind of stops at 0, but it never is actually going to touch 0. So we get really close to 0. So this idea of approaching a number, so if you look in the y direction, we're getting really, really close to 0, right? But we're never actually going to get there. This is an idea that's called an asymptote. Unless we do a transformation to it, like reflections or like sliding it, no. So if you have any sort of exponential function is going to have an asymptote where it can't touch something. And usually that's at 0. So in this case, we have an asymptote. So I like to draw like a dotted line, like, hey, we're going to get here, or we're going to approach 0, but we're never actually going to get there, right? So an asymptote is a line that a graphed function approaches. So this is my asymptote. So once again, we're approaching 0, but we'll never actually get there. So if we have a horizontal line, right, would this be x equals or y equals 0? Does it go through the value of 0 on the y-axis or the x? So I like to think about it as here. It's going through the y-axis, right? So this should be y equals 0. Horizontal lines have y equals, horizontal lines have y equals, vertical lines are x equals, right? The big idea here is just to show you what an asymptote is. It's the idea of approaching a value, but you never get there. So we can draw a horizontal line to represent that. That's kind of the big idea there, okay? If we're given an exponential function of this form, so it's a times b to the x, remember that big difference is the a here out front. It's still the same thing as our parent function up here, but in this case we're multiplying by some constant a. So if we have, once again, some function a times b to the x power, you don't necessarily need to write this. This is an increasing function. Oops, it already says the word function. If it's increasing, the term that you're used to seeing is growth. Once again, if you have a is greater than 0 and b is greater than 1, you're going to have an exponential growth function. So once again, this basically means that the base b has to be greater than 1 for it to be growth, right? If you're looking at the base b and the base is between 0 and 1, this is a decreasing function. So once again, if your base b is between 0 and 1, that's decay. And the idea, once again, think about if you're doubling something, if your base is 2, your doubling means you're getting bigger. But if your base b was a half, you'd be cutting things in half, so it would be getting smaller, right? So decay. Does that sort of make sense? Why it's the way that it is? This letter A out front is just telling you if it opens up. So if it's like opening up, and then if it's negative, it would be a reflection, so it would be down. So once again, tell whether the function shows growth or decay. The only thing we need to worry about is the base. So this one would be growth because b is greater than 1. If I were to give you something like this, oh no, sorry. If I were to give you something like this, though, since this number is less than 1, this would be decay because our base is less than 1, right? That number out front, that's called your initial value. We'll get there eventually. But remember, all you need to do to determine growth or decay is look at that base. This growth or decay function is a big concept in mathematics, and it is denoted by this formula here that I'm going to zoom in on and let you guys copy down. Here. You're always going to plug in the initial amount here. You're always plugging in your rate here and the number of time periods t here to get your final amount here. The big idea, the plus or minus, remember if it's 1 plus r, that's going to be your growth base. And a term that we use for exponential growth is appreciate. My love for my husband grows because I appreciate that he packed my lunch today. And then if you have 1 minus r, that's your decay base, which is also called depreciation. I do not appreciate when my husband leaves the toilet seat up in the morning. So, I don't know. My love for him decays in that moment. Does that make sense? So, the last real thing we're going to have to do for now is, if we're looking at a situation, right, if Clara invests $5,000 in an account that pays 6.25% in interest per year, then after how many years will her investment be $10,000? So this $5,000 would represent your initial amount, which means A, right? I think the tricky part about these story problems is figuring out what you're given. This is my rate, but your interest rate needs to be written as a decimal. So this rate, I'm going to have to move that decimal 2 places back to get 0.0625. And then it says after how many years will her investment be $10,000? That would be your final amount, A of t. So if I were to set this up, I would get something like 10,000 equals 5,000. And then I would have 1, in this case, we're paying, so increasing by 6.25%. Oops. But you need to use the decimal, so 0.0625. And we need to figure out what would that time be. In this case, we don't know how to do this yet, so you'd have to guess and check. But once again, if you were to start plugging in for t, you just plug in 1, see if you get to 10,000. Plug in 2, see if you get to 10,000. Plug in 3, see if you get to 10,000. Takes forever, right? So if I were to ask you, though, how much after 6 years? So we're going to be looking for the final amount after 6 years. Our initial amount was 5,000, right? I have my interest rate that I'm gaining, and I'm going to raise that to the 6th power. Once again, you have to do parentheses, so you get 1.0625, raise that to the 6th power, and then multiply by 5,000 to get your answer. I don't have a calculator on me, but lucky for you guys, I did this earlier. You should get something like 7,193.55. So once again, big concepts here.